Welcome to Sports and Casino Betting. This channel features modeling techniques, data analysis, and statistical methods for analyzing sports and casino games, and is designed for non-mathematicians. We'll discuss each of these topics soon enough. But, before we do, let us take a moment to consider similar sorts of questions that occur outside of sports and casino betting. As the following list makes clear, there are plenty of famous and not-so-famous problems to choose from. While we won't try to solve all of the problems on this list, several are worthy of our attention. We will begin with what might be the most famous probability puzzle of all time. Today's episode is called, Two Goats and a Car. Let's dive right in. To do so, we have to travel back in time. On September 9, 1990, Marilyn Savant, whose 228 IQ earned her a spot in the Guinness Book of World Records for the highest IQ score ever recorded, published her answer to a user question in her syndicated weekly column in Parade magazine called Ask Marilyn, unaware of the tidal wave of anger her answer would provoke. Unfortunately for Marilyn, her column was not limited to a small and affectionate audience. Included as a supplement in numerous Sunday newspapers across the United States, her intelligent musings reached millions of readers. The question she received was loosely based on one of the deals from the popular game show, Let's Make a Deal, hosted by Monty Hall. The letter, sent by Craig Whitaker from Columbia, Maryland, read as follows. Dear Marilyn, suppose you're on a game show, and you're given the choice of 3 doors. Behind one door is a car, the others, goats. You pick a door, say door number 1, and the host, who knows what's behind the doors, opens another door, say door number 3, which has a goat. He says to you, do you want to pick door number 2? Is it to your advantage to switch your choice of doors? By now, you may recognize this problem by its more familiar name, the Monty Hall problem. You may also recall that it was the 5th problem on our list. Let's see if Marilyn was able to solve it. The gist of Marilyn's response to Craig was as follows. Dear Craig, yes, you should switch. The first door has a 1 in 3 chance of winning, but the second door has a 2 in 3 chance. You may think her answer doesn't make sense. If there are 3 doors in one car, isn't it true that there is a 1 in 3 chance the car could be behind any of the 3 doors, and not just door number 1 as Marilyn claims? And if this is the case, which it so plainly appears to be, why switch doors at all? If you're confused, you are not alone. Robert Sachs, who in 1990 was a professor of mathematics at George Mason University, a post he has held for the past 35 years, responded with a fair amount of indignation. Since you seem to enjoy coming straight to the point, I'll do the same, Sachs wrote. You blew it. Let me explain. If one door is shown to be a loser, that information changes the probability of either remaining choice, neither of which has any reason to be more likely, to 1/2. If Sachs had concluded with this remark, he would still have been wrong, but he would not have subjected himself to further embarrassment. Alas, Sachs felt a lecture was in order, adding, as a professional mathematician, I'm very concerned with the general public's lack of mathematical skills. Please help by confessing your error and in the future being more careful. That last sentence hits hard. Unfortunately for Sachs, it was directed at the wrong person. Still, Sachs appears genteel compared to a University of Florida professor named Scott Smith. Unlike Sachs, Smith tried to quantify the size of Marilyn's perceived error. You blew it, and you blew it big, he wrote. Sensing that Savant's 228 IQ made it difficult for her to comprehend what was elementary to him, he continued, since you seem to have difficulty grasping the basic principles at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There is enough mathematical illiteracy in this country, and we don't need the holder of the world's highest IQ propagating more. Shame. I won't read the rest, but they all shared the same condescending tone, with at least one commentator engaging in overt sexism to drum home his point. Let us see if we can make sense of Marilyn's answer. We will begin by writing down the different ways we can arrange a car and two goats behind three doors. The process of arranging a set of items in a particular order is referred to in mathematics as permutations. Although the mathematical formula provides the number of distinct orderings we can construct from a set of three items, it does not tell us what each arrangement looks like. In 1990, the only way to determine all 6 arrangements was by careful construction. Note that the key to this construction is to uniquely place each object, the car and two goats, in each column exactly twice, and only once in each row. For example, the car is the first object in rows 1 and 2, the second object in rows 3 and 4, and the third object in rows 5 and 6. You might think that 6 arrangements aren't necessary, since row 1 is the same as row 2, row 3 is the same as row 4, and row 5 is the same as row 6. The reason for this is because I did not label the two goats as goat 1 and 2. If I had, you would see that the two goats in each row are different goats. To avoid future confusion, I will proceed by representing both goats and the car by square boxes. For each arrangement, we will arbitrarily pick a door, then consider the ramifications of switching to another door or sticking with our original selection. If we wanted to be extra thorough, we could pick all 3 doors in turn for each arrangement, but we can make the same point either way. We begin in row 1 by selecting the first door, which I have highlighted with a yellow background. After we make our selection, Monty has the option of revealing the goat behind either of the other 2 doors. Let us assume he reveals the goat behind door number 3. Thus, if we wish to switch doors, our only option is to switch to door 2. Since goat 1 is behind door number 2, this is a losing strategy. This makes it 1-0 in favor of not switching doors. Next, we consider the arrangement in row 2. This time, we select door number 2, and Monty reveals goat 1 behind door number 3. In this case, if we wish to switch doors, the only option available is door number 1. Since the car is behind door number 1, this is a winning strategy. The score is now tied, 1-1. 2 rows into our experiment, we appear to have confirmed the arguments put forth by our 2 angry professors. Both strategies have been successful half the time. Continuing our experiment, we select door number 3 in row 3 and Monty reveals that goat 1 is behind door number 1. Switching to door 2 is the correct strategy since our initial selection of door 3 conceals goat 2. The score is now 2-1 in favor of switching doors. In the interest of time, I won't continue this process for the last 3 rows. It is easy enough to see what is going on from the graphic. Notice that switching doors is the winning strategy 4 times and not switching doors is successful only twice. Not surprisingly, this is exactly as Marilyn asserted. If so many colored boxes seem confusing, there is a simpler way to view this problem. Notice that a contestant in the game is twice as likely to select a door with a goat than the door with the car. This is because there are 2 doors concealing goats and just 1 door hiding a car. Although I was careful to label the goats as goats 1 and 2, a goat is a goat, and it is always a loser. Thus, when a contestant selects a door, they have a 2 in 3 chance selecting one of the 2 goats. Since Monty will always reveal the goat behind a door the contestant did not select, switching doors will always result in the contestant choosing the door with the car. On the other hand, if the same contestant initially selects the door hiding the car and chooses to switch doors, Monty can arbitrarily reveal either remaining door, as both are hiding a goat. In this scenario, the contestant will always select a door with a goat and lose. But here's the thing, if the contestant always switches doors, they will lose every time they select the door with a car and always win whenever they select a door with a goat. Thus, they will always lose 1/3 of the time, and they will always win 2/3 of the time, just as Marilyn claimed. There is a third way we can test this claim that is worth our consideration as it describes a technique we will use a lot in the future, especially when the problems we are trying to solve are more complex. If you've never heard of permutations, or simply don't understand how they might be applied to solve the Monty Hall problem, you can solve it using the Monte Carlo method in Excel or Google Sheets. The Monte Carlo method is a computational technique that uses random sampling to estimate complex mathematical or statistical problems. It is named after the Monte Carlo casino in Monaco, emphasizing its use of randomness, similar to games of chance. Since I prefer Excel over Google Sheets, I will use Excel for this example. The first thing we need to do is populate our worksheet with a few key items. To begin with, create the header in cells A1 to L1. Next, we will need to add the 6 possible arrangements described earlier. You may enter these in any order. After you've finished, label each row from 1 through 6. Finally, populate column E with the numbers from 1 to 10,000. Next, refer to the table on your screen. Add the formula shown in the table to each cell, or each cell range, as described in the table. Once you've completed this task, you should see results like those shown on your screen. Cell B9 shows how many times switching doors was the winning strategy, and cell C9 shows how many times not switching doors was the winning strategy. These numbers should be close to 6,666 and 3,334. Since random processes are involved, don't be alarmed if your results are not identical to those on your screen. These results will change every time you update the worksheet. You can see this process in action in Excel by clicking in cell A10 to select it, then periodically tapping the delete key on your keyboard. Each time you do, you will observe the spreadsheet being updated. To gauge the consistency of these results, I repeated the simulation 30 times by tapping the delete key as described. The average trial-to-trial absolute difference was 39, which represents just a 0.39% difference. The standard deviation was 47. Overall, the results were excellent. On average, switching doors was the winning strategy 6,666 times. The graph on your screen is a visual representation of these results. Notice how little variation there was from trial to trial. Before discussing the key takeaways from this episode, I want to reconcile the definition of the Monte Carlo method with our methodology. The definition describes the Monte Carlo method as a technique that uses random sampling. Random sampling is a statistical technique that involves selecting a subset of individuals or items from a larger population, with each member of the population having an equal chance of being chosen. This method helps ensure that the sample accurately represents the population, reducing bias and providing reliable estimates of the population's characteristics. At first glance, you may think we did not perform random sampling, and if so, wonder how our simulations serve as an example of the Monte Carlo method. Though perhaps not obvious, we randomly sampled from 2 sets of data. The first set consisted of all 6 orderings or arrangements. Since all 6 were equally likely, we simulated sampling from this set by using the RAND between function in Excel. The second set consisted of all 3 doors, which we also simulated using the RAND between function. Everything else in our spreadsheet was designed to interpret these results. So what have we learned? First and foremost, we learned that experts sometimes get things wrong. In 1990, Marilyn stood alone in a sea of hostility, surrounded by 10,000 angry letters. After writing to tell her she was utterly incorrect as opposed to merely being incorrect, a Georgetown professor asked, "How many irate mathematicians are needed to get you to change your mind?" It was in this moment that Marilyn demonstrated her true genius. She did not capitulate to the angry mob. Perhaps because she recognized that scientific consensus is not the same as scientific certainty, she did not bow to consensus thought. Smart people make mistakes. They sometimes get things wrong. In some instances, as was the case here, they sometimes get things egregiously wrong. When I first encountered this problem in the early 1990s, I was able to figure out the correct probability, just as Marilyn had. Although I did not have the advantage afforded Marilyn by her astronomically high IQ, I had the advantage of knowing she'd solved it. This meant I also had the advantage of knowing that the solution was not trivial. I knew going in that the problem was not straightforward, and that I should discount answers that came too easily. It was only because I knew what to look for that I was able to solve the problem. This is what I find so disappointing about many of the responses Marilyn received. The experts who responded were in the same boat as me. They should have known what to look for. They only needed to prove Marilyn wrong. Why is any of this important? It is important for several reasons, but I will focus on just two. First, it illustrates my previous point that experts can be wrong. They can be guilty of confirmation bias and overconfidence. Like everyone else, they are susceptible to groupthink. They sometimes take shortcuts, causing them to miss key details. And finally, experts can be distracted by other problems they are trying to solve. As the Monty Hall problem proved, experts will sometimes cling to their beliefs in a stubborn or unyielding way, despite evidence to the contrary, and often despite their own highly refined logical reasoning skills. All of the PhD mathematicians who wrote to Marilyn to tell her she was wrong had the capacity to solve the problem as she had, but failed to do so. While their responses to Marilyn were generally harsh, we should welcome such mistakes. To be successful betting on sports, we will need to compete with experts. These experts are the professional odds makers and line makers responsible for analyzing the multitude of factors that go into creating betting lines and odds, including team performance, player statistics, injuries, and public betting trends with the goal of establishing betting lines that balance the money bet on both sides of every wager. These professionals utilize advanced statistical models, historical data, and real-time information. They are smart people. For us to show a profit betting against them, we need them to be wrong. Not all the time, though it would be great if they were, but sometimes. The Monty Hall problem, and Marilyn's solution to it, is important in another way, as well. It teaches us that we need to be meticulous in our problem-solving efforts. Meticulous problem-solving can encompass many factors, but here are just a few to get started. Number 1, never jump to conclusions. While it is possible to look at a problem and immediately figure out the solution, it is unlikely this will occur in cases involving complex problems. Also, as the Monty Hall problem illustrates, some problems are harder to solve than they initially appear. One way to avoid jumping to conclusions is to take the time necessary to clearly understand the problem. A thorough understanding of the problem can help us decide whether the problem is complex, and therefore difficult, or relatively simple. With the emergence of AI and easy access to the internet, you may be tempted to look up the solution to these sorts of problems. While there is nothing wrong with this, you will need to make certain you have a clear understanding of the problem and any concomitant assumptions. This will help you to avoid overgeneralizing solutions that only apply in limited cases. Once you've determined the solution to a problem, it can be useful to use the Monte Carlo method to verify it. This will help to confirm your solution is correct, or it may reveal holes in your analysis or highlight assumptions you did not account for. In this video, I demonstrated how we could tackle the Monty Hall problem by breaking it down into a series of simple steps. I also showed how Monte Carlo simulations can be used to solve this problem. These simulations produced results that varied from trial to trial, and only occasionally matched the values gleaned from our earlier analysis. This will always be true of random processes. Our goal in such cases is to find a solution that is close enough to the actual solution for us to be confident it adequately answers the question at hand. The question in this case was whether to switch doors. It does not matter if the Monte Carlo probability is exactly 66.7% or 66.3% or 67.1%. All three values support the strategy of switching doors. Also, it isn't strictly true that switching doors is a winning strategy 2/3 of the time. This is only ever true if the contestant always selects a door with a go 2/3 of the time. Probabilistically speaking, this isn't likely. For example, if we selected a door 9 times, the probability that 6 of those selections reveal a goat is just 27%. This is an important point. The first two solutions we discussed focused on a single game. The Monte Carlo method, on the other hand, produced 10,000 data points. In future episodes, You will understand why the Monte Carlo technique is a great tool in cases when we want an accurate estimate of some quantity, or are trying to solve a complex problem involving numerous simultaneous events, but lack the mathematical knowledge and tools to calculate an exact solution. In the next episode, we will take a deeper dive into Monte Carlo simulations. In the meantime, consider this problem. Suppose you roll 3 six-sided dice and sum the results. How many different sums are possible and what is the probability of each sum? Although you can easily find the solution to this problem on the internet, see if you can model this problem in Excel before looking it up. To get an accurate result, try running 100,000 simulations. That's it for now. Until next time, good luck in your sports and casino betting endeavors.